Today we will study for quantum mechanics. Photoelectric effect: when a beam of light with frequency equal to or greater than a particular value called threshold frequency is allowed to strike the surface of a metal, electrons are ejected instantaneously from the surface of the metal. This effect is called photoelectric effect. Some important observation about the photoelectric effect as follow. First, the electrons are ejected only if the frequency of the incident light is equal to or greater than a minimum value called threshold frequency. The electrons are ejected instantaneously. There is no time lag between heating of the metal surface by the light and emission of electrons. The kinetic energy of the emitted electrons depend upon the frequency of the incident light. Number 4, the number of electrons emitted is proportional to the intensity of the incident light. According to classical theory, the energy of light depends upon its intensity. Thus, if the surface of a metal is exposed continuously to the light of any frequency, the electrons should keep on gaining energy, and ultimately the energy should become so high that the electrons should leave the metal atom. But actually, this does not happen. However, Einstein explained different observation about photoelectric effect by applying Planck's quantum theory. According to this theory, each quantum of light called photon has energy equal to h mu. H is Planck constant. When photon hits the metal atom, it transfers its energy to the electron. Energy equal to threshold value is used up for bringing about ionizations, release of electron, and the remaining energy is converted into the kinetic energy of the electron. The quantity h mu naught is called work function and is equal to the ionization energy of the metal atom. H mu naught is equal to IE. Thus, h mu is equal to h mu naught plus half mv square. Evidently, if the frequency of the incident light is equal to the threshold value, electrons will be emitted without any kinetic energy. Further, intensity of the light means the number of photons hitting the metal surface per unit time. Thus, increase in intensity increase the number of electrons emitted but will have no effect on their kinetic energy. Equation first can be written in the form Ke, kinetic energy, is equal to h mu minus h mu naught. This equation shows that the kinetic energy of the electron emitted varies linearly with frequency of the incident radiation. Thus, a plot of kinetic energy of the emitted electron versus frequency of the incident radiation will be a straight line with slope equal to the Planck constant h, which is shown in figure 1.6. This gives one of the method to find the value of the Planck constant. Next topic, de Broglie hypothesis, dual nature of matter and radiation. It was suggested by Newton that light is a stream of particles which are photons or called corpuscles. In other words, light is corpuscle in nature. However, this concept failed to explain the phenomena of interference and diffraction, which could be explained only if light is considered to have wave nature. But at the same time, it was observed that the phenomena of black body radiation and photoelectric effect could be explained only if the light is considered to have particle character. Hence, finally, it has been concluded that light has dual nature. Louis de Broglie, a French physicist, in 1924 advanced the idea that, like photon, all material particles such as electron, proton, atom, molecule, a piece of chalk, and a piece of stone or an iron ball, microscopic as well as macroscopic objects, also possessed dual character. The wave associated with the particle is called matter wave or de Broglie wave. The de Broglie relation: the wavelength of the wave associated with any material particle was calculated by analogy with photon as follows. In case of a photon, if it is assumed to have wave character, its energy is given by E is equal to h mu, according to Planck quantum theory, where mu is the frequency of the wave and h is Planck constant. If the photon is supposed to have particle character, its energy is given by E is equal to mc square according to Einstein equation, where m is the mass of the photon and c is the velocity of light. From equation first and second, we get h mu is equal to mc square, but mu is equal to c by lambda, where lambda is the wavelength. h c by lambda is equal to mc square. Lambda is equal to h by mc. De Broglie pointed out that above equation is applicable to any material. The mass of the photon is replaced by the mass of the material particle, and the velocity c of the photon is replaced by the velocity v of the material particle. Thus, for any material particle like electron, we may write lambda is equal to h by mv, or lambda is equal to h by p, where mv is equal to p is the momentum of the particle. The above equation is called de Broglie equation and lambda is called de Broglie wavelength. Thus, the significance of de Broglie equation lie in the fact that it relates the particle character with the wave character of matter. Significance of de Broglie equation. Although the de Broglie equation is applicable to all material objects, but it has significance only in case of microscopic particles. Next topic is Heisenberg uncertainty principle. All moving objects that we see around us, a car, a planet, a ball thrown in the air, etc., move along definite paths or trajectories. Hence, their position and velocity can be measured accurately at any instant of time. However, such an accurate measurement is not possible for subatomic particles. Hence, the existence of definite paths or trajectories for subatomic particles is ruled out. As a consequence of dual nature of matter, Werner Heisenberg, a German physicist, in 1927 gave a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. It is known as Heisenberg uncertainty principle, and it states as follows. It is impossible to measure simultaneously the position and the momentum of the small particle with absolute accuracy or certainty. If an attempt is made to measure any one of these two quantities with great accuracy, the other becomes less accurate. The product of the uncertainty in the position delta x and the uncertainty in the momentum delta p is equal to m dot delta v, where m is the mass of the particle, delta v is the uncertainty in velocity, is always constant and is equal to or greater than h by 4 pi, where h is a Planck constant. Delta x dot delta p is greater than or equal to h by 4 pi. However, for most of the purposes, the mathematical expression for the Heisenberg uncertainty principle is simply written as delta x dot delta p is equal to h by 4 pi. Keeping in view the expression first, the value of delta p calculated for a given value of delta x using the expression second is the minimum value for delta p. Similarly, the value of delta x calculated for a given value of delta p will be the minimum value of delta x. Putting delta p is equal to m multiply delta v, equation first become delta x dot m delta v is equal to h by 4 pi. Delta x dot delta v is equal to h by 4 pi m. This implies that the position and velocity of a particle cannot be measured simultaneously with certainty. It is important to understand that uncertainty principle applies to position and momentum along the same axis. Thus, if delta x is along x-axis and then delta p should also be along x-axis, it is further important to remember that the uncertainty principle is not an account of any limitation of the measuring instrument. Explanation of Heisenberg uncertainty principle. The basis for the above principle may be understood from the following description. Suppose we attempt to measure both the position and momentum of an electron. To pinpoint the position of the electron, we have to use light so that the proton of light strike the electron and the reflected photon is seen in the microscope. Figure 1.11. As a result of the heating, the position as well as the velocity of the electron are disturbed. But according to principle of optics, the accuracy with which the position of a particle can be measured depend upon the wavelength of the light used. The uncertainty in position plus minus lambda, the shorter the wavelength, the greater is the accuracy, but shorter wavelength means higher frequency and hence higher energy. This high energy photon on striking the electron change its speed as well as direction. The next topic is Schrödinger wave equation. In light of de Broglie concept of dual nature of matter and the Heisenberg uncertainty principle, Bohr concept of definite trajectories orbitals failed. Thus electrons not only has particle nature but have wave nature too. Thus like any other wave, it would be possible to express the motion of the electron in terms of an equation called the wave equation. The derivation of this equation was carried out by Schrödinger in 1926, making use of the de Broglie relationship lambda by my h by my p, which therefore may be called the essential postulate of Schrödinger wave equation. The derivation may be carried out as follows. Consider the simplest type of wave motion like that of the vibration of a stressed string traveling along the x-axis with a velocity v. If y is the amplitude of the wave at any point whose coordinate is x at any time t, then the equation for Schrödinger wave motion is del square y by my del x square is equal to 1 by mu square del square y by my del t square. This differential equation indicates that the amplitude y of the wave at any time traveling with a particular velocity depend upon the displacement x and the time t. In other words, y is a function of x and hence t. Hence, we may write y is equal to function of x f dash t, where fx is a function of coordinate x only and f dash t is a function of time t only. But the stationary waves as occur in the stretched string, we know that f dash t is equal to a 2 pi mu t, where mu is the frequency of vibration and a is a constant equal to maximum amplitude of the wave. Substituting the value of f dash t from equation 3 in equation 2, we get y is equal to fx a sine dot 2 pi mu t. Differentiating this equation twice with respect to t, we get del square y by my del t square is equal to minus fx 4 pi square v square a sine 2 pi vt is equal to minus 4 pi square v square fx f dash t. Differentiating equation second twice with respect to x, we get del square y by my del x square del square fx by my del x square f dash t. Substituting the value of del square y by my del t square and del square y by my del x square from equation 5th and 6th into the equation first. We have del square fx by my del x square f dash t is equal to minus 1 by v square is equal to 4 pi square v square fx f dash t. Del square fx by my del x square is equal to minus 4 pi square mu 4 pi square v square by my mu square. This equation has become time independent and hence represent the variation of the amplitude function fx with x only. Further, the velocity v is related to the frequency mu and the wavelength lambda of the wave by the expression mu is equal to v lambda. Substituting this equation is in equation 7 we get del square fx by my del x square is equal to minus 4 pi square by my lambda square fx. This equation has been derived from the wave motion in one direction only. For extending the equation to the wave motion in 3 dimensions, the amplitude function for one coordinate may be replaced by psi xyz or simply written as psi for the sake of brevity, which represent the amplitude function for 3 coordinates. Thus the equation for wave motion in 3 dimensional will be del square psi by my del x square plus del square psi by my del y square plus del square psi by my del z square is equal to minus 4 pi divided by lambda square psi. Now the postulate is introduced that this equation is applicable to all particles like electron, nuclei, atom, molecule, photon, etc. Further introducing applicability of de Broglie equation as another postulate according to which lambda is equal to h by mv, where m is the mass of the particle, v is the velocity and h is the Planck constant. Equation 10 become del square psi by my del x square plus del square psi by my del y square plus del square psi by my del z square is equal to minus 4 pi square m square mu square by my h square psi. Further, we know that total energy of the particle is equal to kinetic energy plus potential energy. E is equal to half mv square plus v, or half mv square is equal to E minus v, where v represents the potential energy of the particle. Substituting the value of mv square from equation 12 in equation 11 we get del square psi by my del x square plus del square psi by my del y square plus del square psi by my del z square plus 8 pi square m E minus v by my h square psi is equal to 0. This equation, which represents the wave motion of the particle in 3 dimensions, is called Schrödinger wave equation. The next topic is postulates of quantum mechanics. The derivation of the Schrödinger wave equation as given in section 1.19 was based upon the concept that the electrons have wave motion. However, the Schrödinger wave equation can be derived without making use of this concept, but on the basis of certain postulates called the postulates of quantum mechanics. These are of follow. Postulate first: for every time independent state of system, a function psi of the coordinates can be written which is single valued, continuous and finite throughout the configuration space. This function describes completely the state of the system. Postulate second: to each observable quantity in classical mechanics like position, velocity, momentum, energy, there corresponds a certain mathematical operators in quantum mechanics, the nature of which depend upon the classical expression for the observable quantity. For example, the operator corresponding to a position coordinate is multiplication by the value of that coordinate. Operator for a position coordinate is the multiplier x. Postulate 3: If psi is a well-behaved function for the given state of a system and A is a suitable operator for the observable quantity or property, then the operation on psi by the operator A gives psi multiplied by a constant value, say A, of the observable property. The given state A psi is equal to small a psi. The given state is called the eigenstate of the system, psi is called the eigenfunction, and A is called the eigenvalue, and the above equation is therefore a general expression for the eigenvalue equation. Postulate 4. The only possible measured value of an observable are the eigenvalues obtained from the eigenvalue equation given in postulate 3 above. Thus, if the wave equation psi of the system is an eigenfunction of the operator for the observable, then measurement of that observable gives eigenvalue. If the wave function psi of the system is not an eigenfunction, then the value of the observable obtained on measurement has a probability that can be calculated from the wave function. Postulate 5. If a number of measurements are made over the configuration space, then the average value of the quantity represented by A bar is given by A bar is equal to total integration of psi star A psi d tau divided by total integration of psi star psi d tau, where total integration represent integration over the whole of the configuration space. The basis of this postulate is as follows. From equation first, A is equal to A into psi divided by psi. But this expression will not give a constant value of A because it involves the function of the coordinates which vary from space to space. By multiplying the numerator and denominator by the complex conjugate psi star and integrating over the whole of the configuration space, the result obtained is no longer a function of coordinates and give an average value of the constant A.